Okay, hello everyone. My name is Meng from Hong Kong University of Science and Technology. Today, I'm going to share our work MAE. We want to achieve the consistent low latency in real-time communication. Let's start. So first, the real-time communication has been one of the key uses on the internet today, including the online meeting, the video calls, cloud gaming, and the future maybe remote surgery. The data shows that the current market has reached more than 11 billion in 2024. This shows the market is huge and the users are passionate. But the current store experience are still far from satisfactory. Have you experienced this? When you are in an online meeting, you are full of passion to talk about some ideas, or maybe how to write a good paper. But you don't get any response. After a few later seconds, you heard from the other side, sorry, you are lagging. This is very upset, right? So, and the large-scale online data also shows that the 99th percentile tail latency is more than 200 milliseconds. 99th percentile sounds like not that common, but in RTC, it means every 1,000 frame will experience a stall, and that means every 30 seconds. This is not acceptable. So here comes a question. After the more than 20 years development, why current stall issue didn't be solved? And to answer this question, I want to first introduce how the RTC pipeline works. This shows a basic, it's like a water pipeline. The encoder as the source will encode the original data into smaller size and transmit through the whole pipeline, like the water, and finally reach the receiver. The average latency of current RTC is almost around the 20 milliseconds, which is satisfied for the users. But because the network is shared by all internet users, it's always fluctuated. Sometimes its bandwidth will drop even up to 50 times. This gives us a challenge because when the out stream is reduced, what will happen? The data will accumulate in this network, which will cause the delay spike because all the packets are waiting to be transmitted. Here are many works trying to solve these problems in the different network components, but they didn't fully solve this problem. And why? The answer is because, let's take the router as an example. The works on the router, they will make the routers more sensitive to the network change. When the network bandwidth is reduced, it will more sensitive to it and quickly adapt to it. But as a water pipeline, if you pinch on some middle part, you can only control the following part. That is, it can drain out the accumulation in the following the network, but you don't have the control about the upstreams. The data will continue accumulated at your pinch point. This means you didn't solve the problem. You just shift the waiting quiz from the downstream to the upstreams. So here is our key insight. As long only if we reduce the source about the whole pipeline. It's like a water tap. Only if we reduce the output about this water tap, we can truly solve this latency issue. But this encoder, this source, is highly overlooked currently. And what is the current reaction speed to the bandwidth drop of existing encoders? Unfortunately, the answer is they will, for all the commercial encoders, they will take more than 200 milliseconds to react. This will cause up to 800 millisecond latency. Very amazing, right? And we also did the experiment on the WebRTC. We want to know that which part really dominates the reaction time. The result shows that more than 77% comes mainly from the encoder. And why the encoder takes so long? We also let's understand why the encoder will take this long time. Let's dive into a detailed bandwidth drop adaptation process. From here, the router sends the drop, and from some time later, the socket began to sense the drop. And from here, the socket will tell the encoder it's time for you to drop the bandwidth. Why the router and socket need this time window? Because the bandwidth is always fluctuated. We cannot be oversensitive, otherwise we will underutilize the bandwidth. So this process is normal and accepted. The key thing is for the encoder, it will take so much long time to slowly react. And at this time, the encoder will finish the job. Not only this will cause a huge encoder reaction time, but it also needs more time to recover from this high latency. And why current encoder reacts so slowly? The answer is because current encoders are treated as a total black box. The network only gives the target bitrate for encoder, and the encoder can only based on this information to decide the output frame. What our network people expect is we give the target bitrate. The encoder output just what's the exact frame size. But the question here is the content is always fluctuated. For example, the first and second frames are almost the same, but the third frame, it has a highly complexity. If we keep the same frame size for all these frames, it will lose some bytes for these static frames and to lose some details on these high complexity frames. So the real frame size is something like this. The high complexity frames will use some bytes about the static frames. Through this way, we can achieve a higher quality for all the frames. And how the encoder to control this overshoot, because we can see some frames avails overshoot the target bitrate. The answer is the encoder will use virtual buffer to control the overshoot. So the virtual buffer, its goal is to maintain a higher quality by adaptively to shift some bytes from the static frames to the high complexity frames. Let's see how the virtual buffer works. This orange block shows the virtual buffer. It gives the information about how many overshoot ability the current frame can use. And basically, it will repeat this process to guide the whole encoding. And in this time, because it's high complexity, the frame wants the more frame size more than the virtual buffer. The encoder will say, no, you can only use this. This is how the virtual buffer works. And what will happen when network bandwidth drops? The answer is both the virtual buffer and the target bitrate will also adapt to the new network. We can see here. But even the virtual buffer reduced, it still allows some overshoot. This overshoot is accepted when the bandwidth is stable, but when the bandwidth drops, all these overshoot frames will cause a huge delay accumulation, which causes the delay spike. So this means the current adapt about the encoder is not enough. We need a more adaptive encoder, which is our solution, MAE. So the first part of our design of MAE is dynamic virtual buffer size. Let's still see this figure. This shows that if we use an always large buffer, it's good for the quality, but it will cause a delay spike. The next very intuitive idea is that how about we just limit the virtual buffer exactly equal to the target bitrate? That means we don't allow any overshoot. This can control a smooth delay, but the question is for those high complexity frames, it will be reduced the quality. So the latency is good, but the quality is bad. Our solution is more adaptive to the network condition. For the network is stable, we use a higher virtual buffer to maintain the quality. As long as we sensed here is a bandwidth drop, we can reduce the buffer to exactly the target bitrate, avoid any overshoot. This will quickly drain out the accumulated delay and to keep the smooth experience. After we sense that the current latency is under control, we can recover the buffer size to the larger to maintain the quality. Here, let's back to this detailed bandwidth adaptation process. After we quickly react the encoder, from here, it can avoid the whole delay accumulation process. It can directly into the recovery time. So the reduced latency is very huge. And the next is, we know that the encoder needs to more adaptive, but when the encoder reacts to this adjust, only based on the target bitrate, based on the trend, is not enough. Our solution is current congestion control algorithm. They have the potential. They have the internal state to guide the encoder to react. So first, let me introduce the CCA basic process. So the CC will take the feedbacks from the network, and this will have the latency, this matrix. Based on the past latency, the socket will decide the target bitrate, not only for encoder, but also for the output rate to send the packet out. And current CCs will have a threshold internal to guide this process, because they don't want to over-sensitive or they don't want to miss some. So how to design this threshold is very important in CCs. And this gives us the opportunity that we already have this threshold. What if when the latency larger than the threshold, we will give a signal to the encoder. Because the CC has been developed for many years and we believe that they are mature. So to reuse the internal state of CC can save us a lot of effort. And what's more, maybe the further step, if we can use the threshold to signal, how about we reduce the threshold? We use a half threshold, then we can pre-react to the potential bandwidth drop. And here comes a question. Why we can use this potential drop signal, but we cannot directly reduce the original threshold? The answer is the first, because the original threshold is not only for encoder, but also guides the output. And if we directly reduce it, it means the output packet stream will also be reduced, which will underutilize the whole bandwidth. And the next answer is the directly reduced threshold will not only affect the output rate, but also the encoder's quality. Because if we use a lower target bitrate, also it's accompanied with lower virtual buffer, it will reduce all the quality about these frames and also the following frames. But if we only use this signal and only adapt on the encoder, it will only to limit some overshoot ability of these frames, which can maintain a higher quality. Let's still back to this figure. Through the pre-reaction, we can further reduce the latency, but here, we can directly to limit the overshoots. So from this after the pre-react process, you can see the encoder won't to overshoot that much, so it will not to cause the delay still accumulate. It will be a little bit smooth, and then after the real drop signal happens, it will begin to drop. This is a result about our MAE's performance. The x-axis is the latency and y is the quality. We want to achieve the low latency while maintaining the quality. We can see that MAE can outperform all the baselines. We test it on the WebRTC and across the diverse networks, including Wi-Fi, Ethernet, and cellular. And for the store ratio, we can reduce the 86% store ratio. And compared to the conservative solutions that we do not allow any overshoot this solution, our MAE can achieve the 11% quality gain. Also, maybe some people will concern that will MAE bring some overhead because maybe we need more reaction. The answer is fortunately no, because the MAE do not need to modify any encoders or the CC or the protocol. They just to reuse the current the the ability. So for the CPU memory or the encoding time, they are the same with the benchmark. Also for the bandwidth utilization, at most we only reduce for the 4%. It's also a CCA agnostic integration. We also extended our MAE to the COPA, and it reduced the 47% store ratio. And here are some takeaways. The first, our key insight is the slow responding encoder is the core bottleneck behind the existing playback stall. And the second is the current encoder has ability to control this, but to treat it as a black box is underutilize this all potential. The third is the current CC also has the potential to indicate the other component, the potential bandwidth change. The final is our MAE framework requires no modification to the existing encoders, congestion control algorithm, or the network protocol, but it can reduce the store ratio by 86% while keep the same quality. Thanks for your listening and welcome to any questions.